So today we're going to talk about the periodic table and how it was developed and how we can use it. So in 1860 there were 60 known elements, and that's significant because that was about the time that the first technique for determining the relative sizes of atoms was developed. So at that point, if you think to your card activity, from 1860 on, we could put the elements in order by atomic mass, like you did in your card activity. So once you did that, once you established the order by mass, then you could start to look for patterns. And that's exactly what chemists did for about 9 years until 1869, when the first one to successfully figure out the patterns within the periodic table, or to develop a periodic table, Dmitri Mendeleev came along and used what's called periodic law to create his periodic table. That just means that the properties of the element, like melting point, boiling point, conductivity, reactivity with oxygen, all those properties are a periodic function of atomic size. And so that's called periodicity as well. It simply means that, instead of just being a function, i.e. going up, like the melting point doesn't just go up from the smallest element on, it might go up and then come back down and go up again, right? So we saw that with your activity. Okay, so the Mendeleev's periodic table, a couple of key things about it. It predicted some undiscovered elements. He was able to actually predict the existence of a few elements that hadn't been discovered yet and their properties. In other words, missing elements. His were ordered by atomic mass. The modern one uses atomic number, which wasn't developed until about 1911. A guy named Henry Moseley was able to figure out the number of protons in each atom. Once you do that, you realize that Mendeleev was right about his order for the most part, and that elements that looked like they were out of order according to atomic mass were actually in perfect order when you wrote down their atomic numbers. His groups or families ran horizontally, whereas the modern one has groups or families of common characteristics running vertically. And he had no noble gases on his periodic table, which makes sense because noble gases are unreactive, and so they weren't discovered for several more years after that. This picture you can see, this was a German printing actually of Mendeleev's periodic table. Mendeleev was Russian, but this was an early German printing. You can see some of the missing elements, these little question marks. So if you look at a periodic table, a modern periodic table, below carbon and silicon, and above 10, you would have germanium. And he was pretty close to the true atomic mass of germanium. He also predicted its properties. Did the same thing with gallium, which was located right below aluminum and boron on the periodic table. So he was able to be remarkably accurate with elements that hadn't been discovered and in some cases wouldn't be discovered for years. All right, the modern periodic table, the groups or families are running vertically. So you have groups, 1, 2, all the way up to 18 running vertically, and those are all elements with common or similar characteristics. We sometimes refer to the S in the P block, the groups 1 and 2, and then 13 through 18 they're called the main group or sometimes representative elements. If you hear the term transition metals, that typically refers to the D block, which are groups 3 through 12. Sometimes also a little bit of the lower left part of the P block, which would include like tin and lead. The lanthanides and actinides are the bottom of the chart. That's the F block. And it is important, of course, we've mentioned this a couple of different times in a couple of different ways, but members of the same group have similar physical and chemical properties. And then another term that you need to be familiar with is that the horizontal rows on the modern periodic table are often referred to as periods. Okay, some important groups here. So you should know where the metals are on the periodic table. They make up most of the periodic table, so what you see here in green. If you draw a diagonal line roughly from upper left to lower right of the P block, that diagonal line will sit on the metalloids, which we'll talk about in a second. Everything to the left of those metalloids are metals. okay, except for hydrogen. Everything else to the left of that diagonal line of metalloids are the metals, okay? And it will become important that we understand the difference between, where we find metals and where we find nonmetals in the periodic table later on. All right, they tend to be malleable, which means you can hammer them into new shapes and flatten them out, things like that. Ductile means they can be stretched thin like a wire. Conductive of heat and electricity as well. Metalloids have intermediate properties, so that's like boron, silicon, this whole diagonal line. You don't have to memorize exactly what they are, which ones they are, but silicon is probably the best to use as a representative metalloid because it's shiny and silver colored, but it's brittle. It's breakable. Unlike a metal, which of course when you hit it with a force, it's malleable. It's also a semiconductor, so it's somewhat conductive. So they have intermediate properties. And then finally, the nonmetals. These guys make up the rest of the periodic table. Most of them are gases. So like all the noble gases are, of course, gases. Chlorine, fluorine, oxygen, nitrogen, those are all gases. There are a few that are solids: carbon, phosphorus, sulfur, selenium, iodine. Those are all gases. I'm sorry, those are all solids. But most of them are going to be gases at room temperature. If they are solids, they're not going to be metallic, of course. They're going to be non-conductive. They're going to be dull. They're going to be brittle. Okay, we're going to take a look at these in class later on. The alkaline metals. These are very reactive, and they're also very soft. These are metals that you can actually cut through with a knife, and they will react very easily to give up their one electron in the outermost energy level that is in the S sublevel. We'll talk about that more, a little bit more when we actually watch this reaction in class. Group 2, the alkaline earth metals, are almost as reactive, not quite, but still pretty reactive. These guys have 2 electrons in the S. So for example, magnesium ends in 3s2, and those 2 3s electrons are very easily lost. And so those are pretty reactive as well. Jumping all the way over here to group 17, the halogens. Those are another significant group because they're also very reactive, but for an opposite reason. They don't tend to lose 1 or 2 electrons, they gain 1. So chlorine or fluorine, these guys are very good at gaining an electron to fill up their outermost shell. And they're so reactive that they don't exist as lone atoms. So when you talk about chlorine gas, it's always going to be Cl2. The same thing with fluorine and all the halogens. And then finally, the noble gases. The noble gases are significant, and they're called noble gases because they don't mix with other elements because they don't need to react. They already have filled S and P sublevels in their outermost energy level. Okay, so they already obey the octet rule, which we'll talk about more later. But they're very unreactive. They're very difficult to detect because they're so unreactive, and they're also colorless and odorless and all of that. So they are already basically completely stable.